Okay, so this is the Advanced Cryptography course. It's split into 6 main units. What you'll find is that the main website is here, securitySite.com/crypto, and you should find many of the examples there too. Okay, so the 6 key units that we'll be looking at. In this one here, we'll be looking at some ciphers, some old-fashioned ciphers of cracking and so on, some of the basic methods that we might have used in the past to be able to keep things secret. Then we'll look at some encoding methods, especially in ASCII, FTF16, base64, hexadecimal, and so on. Look at the different formats that we represent numbers and characters with. Then we'll look at key concepts around prime numbers, the greatest common denominator, and also large numbers. We use a concept called big integers in cryptography. And then on to random number generators. We'll have a look at some basic integrity methods such as CRC32, a basic frequency analysis, some key-based encryption, and then key sizes. And then we'll go on to look at the public key, private key and key exchange, and the third unit will look at hashing and authentication, then on to digital certificates and signing, and the fifth unit will look at disk encryption, encryption cracking, and some vulnerabilities, and then finally we'll look at tunneling, email, and secure Wi-Fi. Okay, so that's the basic layout of the course, and it's quite a fast pace, so be ready. But all the examples are on the site that you can actually have a look at. Okay, so I'll just show you the site. Here we are here. So as security site, crypto, we'll be using methods around encryption and also with encoding. Okay, so today we'll look at ciphers and some fundamentals. Okay, so as part of this unit we'll be looking at, as we said, ciphers, encoding methods, some prime numbers, the greatest common denominator, large numbers, and so on. Okay, so here we have, this is our basic infrastructure. In cryptography, what we have is Bob and we have Alice. We'll be coming across them in more detail in later units, and what we really want to do is to allow them to be able to communicate and identify each other, and also for the data to translate over a network without Eve really getting involved. So Eve could pretend to be Bob, Eve could change Bob's messages, and so on. Okay, so our challenge is really to make sure that they can communicate together. So sometimes we need another actor here, and we have Trent, and Trent is our trusted third party. What we've done though is that we've created an infrastructure which is fairly insecure. Our data is stored insecurely often. The network protocols that we use are also typically insecure. So increasingly we're using cryptography to be able to keep everything secure, but increasingly also to identify entities, either people or data, and so on. So identity is actually quite an important factor in security. Okay, so we'll come on to these protocols a bit later in the course, but generally we're moving away from these old protocols towards new ones which use cryptography to keep things secure. These old ones were really created in a time when we had text inputs and people typed commands into a terminal, and security wasn't really a major issue. Now it is, and we need to migrate away from these basic insecure protocols towards the new ones. We also need to make sure that data has end-to-end security, so it's not just in the transit of the data, actually it's in the data itself as it's stored or even analysed. So increasingly we're using cryptography with inside the memory of devices, and even with inside mobile phones. The latest iPhone iOS actually has cryptography built into it and uses encryption by default. And as we go through the course, we'll actually see these are some of the people who have really influenced the whole subject area. Whitfield Diffie we'll find was involved in key exchange, especially in creating the Diffie-Hellman method. Rvesh, Shamir and Alderman created the RSA method, still highly valid today, and they came up with the first real public key encryption method. And then Ron went on to create many hashing methods, as we'll see, MD5, MD2, MD4 and so on. And we have Phil Zimmerman, who created secure email with PGP encryption, and Bruce Nair, who's really influenced the whole field, who came up with Twofish and Blowfish and so on. And then we'll see these two chaps here who came up with Raindal, or AES, which is now the standard in private key encryption. Okay, so let's have a quick look at some ciphers and see if we can actually see where we've came from and how we can get into the mode of cracking things. Okay, so here's some of the original methods that might have been used to keep things secret. So this is a microfiche, where documents were reduced down to a very small size and could actually be transmitted fairly secretly between two entities. Then we have the Navajo code talkers in the Second World War, who created a code that was almost uncrackable. Then we obviously see things like smoke signals, which were used to pass messages between two tribes. And then we have things like this, which is a quilt, which actually has a secret code to actually show the slave how to actually escape from their entrapment. So what we have is that we have Bob and we have Alice, and then we have A in between. So one way that we could do this is to be able to encode with a special algorithm. Okay, so there's the encoding here, and then we send it over. As long as Eve doesn't know what the encoding algorithm is, then if Alice knows about it, then she can decode it because she knows how to do the reverse of it. So that's our basic method to be able to communicate securely. One of the first techniques was Morse Code, and Morse Code uses a series of dots and dashes to represent the codes. It's not a secure method, but it's a way that we can represent our data. And we can think of these as ones and zeros, really. An E is just a small dot, and then an S is 3 dots, and so on. So here we go. 4 dots is an H, an E is 1 dot, then an L is a dot, dash, dot, dot. Actually, this is a message here. So let's see if we can actually find out what that message actually is. So if we look at it, that's an N. This one here is U. This one is an F, and that one's a C. Newcastle United Football Club. That's what that says. Okay, and we can also get little bracelets with Morse code actually on them there. Okay, so it's a very simple method to be able to transmit, and you can have a look at this page up at the top here to have a look at some of the coding used. And then we have a Polybius, which was a grid code that we used. So the most popular letters are laid out in a grid. We have 26 letters, so one of them needs to be borrowed. So we have two characters fitted into this grid space here. And then we just look up the grid. It's fairly easy to write the grid out. So for hello, we have 2 and a 3. And then for an E, we have a 1 and a 5, and so on. Okay, so fairly simple type of code. A useful code is Pigpen, and Pigpen allows us to be able to draw out our code. We have a G here, just missed off, and we represent each of the characters where they are in the grid. So you see there's dots here, and then there's a different shape over here. So if we wanted to represent this word here, then that's a square with a dot, which is an N. This one here is this shape here, that's an A, and then this shape is here with a dot, and that's a P, and we should find that that's IER, Napier. Okay, so A good method for coding, creating a little cipher, and obviously it's fairly easy to remember for that. And we can see the Freemasons actually used it for their cipher, and there's the headstone of James Leeson, and it has a big pen code around there. Okay, so as part of the tutorial for this part of the presentation, you can have a go at some of the codes. Then we see ones such as an ADFGVG code, which is used in World War I. In this case, we just take our grid, so an F and a D gives us a K, and a V and a G gives us an I, and so on. And then we see more complex codes, such as Playfair, which was actually invented by George Wheatson. What we do is we create a 5x5 grid, and then we have a special code that we write out first. In this case it's Napier Run. After that we lay out each of the characters so that they don't actually repeat. So we already had an A, so we do B, C, D, we've already had an E, F, G, and so on. Then what we do is that we draw a rectangle around, we take each character two at a time. So if it's attack, then we have an A and a T, and we draw a square around it, and then we pick off the two characters at the outer edges, in this case E. Okay, if the characters are in the same column, then what we do is that we take one letter below and the current letter, like this one here. Okay, so TA is a square here, and then that becomes an E and an M. Okay, so in this way we can actually create our code. Okay, so what is that? Well, obviously that's an I, and then it's an N, and we have a K. So I think this is Inkwell, so you can see straight away you can get your code from there. Okay, so have a go with that one. So D A is an L, and a D and a G takes you to there. So we've cracked already. Slow them. Then for the Playfair code, an H and an E. So H and an E. This is P and an L. And one of the first proper cipher codes that was created was actually created by Caesar and defining a Caesar code, where he took the alphabet and then just moved the characters on by a certain number of places. So in this case what we have is plain text, and we'll represent that in lowercase, and then ciphertext will represent that in uppercase. So in this case we've moved 1, 2, 3 letters along, so an A becomes a D, and so on. So a K in this case is an H is an E, and then an O is L, and then an R is O. Hello. Okay. The number of codes that we have here is only, unfortunately, 25, so it doesn't take too much to actually crack this type of code. And it was actually used and by this chap here, who didn't want to use complicated encryption methods because they were the non-believers code, so he used a basic cipher code to store his messages. Okay, so we can have 26 codes, or really 25 unique codes, because one will repeat again. Okay, so we've seen that one, and that one was hello. A more complicated code and actually quite a difficult code to crack using different permutations, is actually the scrambled alphabet. In this case, we've scrambled it up, so an L is an I and a Q, and a Q is a bit difficult to find. Q is an end, N, and so on. So in this case, we actually have 26 factorial codes, and that's actually almost uncrackable by a computer, a fast computer, because there are so many codes to try out. And here are the number of codes that you actually have for that. So we need to use a smarter method to be able to crack that type of code. And what we do with plain text is that we do a frequency analysis where we know roughly the probabilities of the letters. E is the most probable letter, and then what we would do is find the most probable letter in our ciphertext, and there's a very good chance that that relates to an E. So we've got T, O, N, and so on. We then look at 2-letter words, 3-letter words, and words themselves, and we can do a basic frequency analysis of that. So you should find that we have a little challenge for you. So a good target for this is to complete this in 5 minutes. Okay, so 5 minutes you have to crack this piece of text. And let's just have a look at that. Okay, so we're going to go to our scrambled . Okay, so I'll just show you how to start it. So here we are here, that's the code that we need to crack. So this has done a basic frequency analysis, so we can see normal text, there's the E, your text here. So it looks like an S is an E. So what we would do is that we take the S and then we would translate that to an E. Okay, make sure you put it into lowercase, and then it will show here. So let's take a pop at this. I think that looks like the here. So a P becomes a T, and a D becomes an H. Okay, so you should find that it will start to make sense the more that you analyze it, and from there you can actually crack the code. Okay, so that's a frequency analysis. And then another code that we get is the Vinegar Code. With the Vinegar Code, what we have is a secret keyword, and then we create a grid with the alphabet, and then we move down the alphabet depending on the keyword. So in this case we have an H, and the keyword is green, so we go down to the G, and it becomes an N. Then we have a keyword of E. We have an E and then an R for the keyword, so it becomes a V, and so on. So the great advantage with this code is that it doesn't actually repeat the letters again, as long as we're changing the letter with inside the key. Okay, so again we've got a little Vinegar Code calculator for you to try out. For something that's uncrackable, then we can have what's called a OneTime Pad. With that, Bob and Alice actually have the same codebook, and then Bob just actually sends through the character numbers, and Alice actually goes and looks that up. Okay. So in this case, Shetland becomes character 198. So that's character 198. In this case will be the S, and so on. And then if we want to make sure that the intruder doesn't do a frequency analysis, then we can use what's called a homophonic code. In this case we use more codes for most popular letters and fewer ones for the least popular ones. So we should find that we have an equal balance when we look at the frequency analysis of the bytes in this case. Okay, so in this case we can see an E actually becomes different characters then, different byte sequences. Okay, so let's look at the next part of this this unit. We're going to look at various encoding methods. So what we have is that we have normally we have characters. The characters themselves is what humans understand, but really computers only understand ones and zeros. So that is translated into byte values, and A is represented by this byte value. And then we might encrypt it, and we end up with ciphertext. Unfortunately, the ciphertext is very difficult to view because it will change into characters which aren't viewable. So we often represent them in terms of hexadecimal or base 64. So if we have a quick look at what that looks like, we'll look at our coding here, and we're going to have a look at this one here. Okay, so there's our character A, and this is how we represent our characters. There's binary, there's the hexadecimal value, and there's base 64. Okay, so these two conversions, hex and base 64, are very important. In hexadecimal, we take our byte values and we split them up into 4 bits at a time, and then we convert them into a hexadecimal character. So hex goes from 0 to 15. So from 9 onwards, we go to A for 10 and then F for 15. So we only need to count up to 15 to be able to do this. So this is a 1, no 2s, and a 4, so it becomes a 5. This here is a 14, a 2, a 4, and an 8, 14, which becomes E, and so on. So then our bit stream can be represented in this format as hexadecimal. So typically we put 0x in front of a hexadecimal number to represent it as hex. The other method that we use is the typical method that we use when we're transmitting especially binary data, is to use base 64. With this we take 6 characters at a time. 6 characters at a time. And then we look up the value. So in this case, this is a 1, 2, 4, 8, and a 16, which gives us 25, and that becomes a capital Z, and so on. Okay, so we can actually have a look at that. There's our base 64. And our translation goes into that. Another operator that we'll see fairly extensively is the exclusive OR operator and the rotate. These are very simple operations, but they allow us to be able to create our cryptography. So with exclusive OR, a 0 and a 0 gives us a 0, a 0 and a 1 gives us a 1, 1, 0 gives us a 1, and a 1 and a 1 gives us 0. A bit like a binary counter. So 1 and a 1 gives us 0, a 1 and a 0 gives us 1, and so on. The great thing with exclusive OR is that we can take the same value back again, exclusive OR again, and what we get is the resultant. So we never lose any information. The other operator that we have is the rotate left and rotate right. So rotate left will take the bits that way, and then anything that drops off the edge goes on the other side, and so on. So again, we never lose any of our information. The cryptography that we have, typically we use these two operations to be able to scramble the data. Then something we'll see fairly extensively is the usage of the mod or modulus. So with this we take a divide and then we take the remainder of it as the result. So 143 mod 5 becomes 28, remainder 3. So we're only really interested in the remainder, so that becomes 3. Okay, so you should find that your calculator contains mod on it. 143 mod 5 gives us 3, and so on. Okay, so work out what that value is there and see if you can get the answer to it. The other thing that we have is that we have different representations for our characters. The standard format is ASCII, that's 7-bit, but we often use 8 bits, and we can represent that in a hexadecimal format. This is 44 and a 1. This is 42, 4 and a 2. Okay, so a capital A is hexadecimal 41 and a B is 42. We can also represent that in a decimal value. That's 65 is the decimal for an A, or in an octal, or also in an HTML type format. Unfortunately, ASCII only gives us about 125 and 256 characters. We need more, then we use a different encoding format such as UTF-16. So let's have a quick look at what that looks like. And this format, there's our standard ASCII table. Okay, so 32 decimal is a space, that's a 20 hex. The characters start here. Well, the main alphabetic characters, 65, 41. And there's the lowercase one, 97 or 61, only changes with 1 bit. And our UTF-16 has many characters in it. Okay, and they're represented by 16-bit values. Okay, so we can get lots of different symbols that we can actually represent. So increasingly we're using this to be able to represent our whole range of characters and different alphabets and so on with inside there. But from 0 to 255 it's actually just the same as our ASCII. It's just that there's a whole lot of zeros actually in there. So we've got non-printable characters that you don't actually see. 13 is a new line, and 10, 7 is a tab, 8 is a backspace, 20 is a space, that's a printable one. Okay, so we have different formats for our characters, and we can actually have a look there again, just to show you that. So there's our ASCII, there's an A61, there's a base64 format, and there's the binary format. Okay, octal counts up to 8, and we take 3 bits at a time. And so now let's look at some key concepts that we have within cryptography, including prime numbers, large numbers, big integers, and the greatest common denominator. We'll be using these principles later on in the course. What we have in cryptography is that we've got to make it difficult for computers to crack our messages. So the two ways that we do it is either have lots of keys, so even a computer will take too long to be able to try all the different keys to be able to open the locks that we create. Otherwise we create a mathematical challenge which is actually quite difficult for them, and in this case we take two prime numbers together, we multiply them, and then it's actually quite difficult for the computer to find out what the original prime numbers were that actually created the multiplication. So those are the two main ways that we can actually defeat our computers. But increasingly we've got to keep increasing the sizes of number of keys and also the sizes of these prime numbers to be able to defeat them. Okay, so a key technique that we have is what's called a prime number. And a prime number, you should all know from school, is a number that is only divisible by itself and 1. So 2, 3, 5, 7, 11 and so on are prime numbers. So the way that we defeat the computer is that we take two prime numbers, we subtract 1 from them, we multiply them together, and it's actually quite difficult for the computer to be able to crack, to find the original primes back again from that. It's a very challenging task. So in this case, what's the primes of 12? Well, actually 12 becomes 2 times 6 or 4 times 3. So that is 3 and 7 would have been the original P and Q values to create 12. Okay, so you should find that there's an example of this on the cryptography page. If you look at our primes, okay, so they're generating 2 prime numbers, and then that's the multiplication together. These are quite small primes, just to actually show you the values there. The other concept that we have is what's called the greatest common denominator. So that is the largest value which will divide into both of them and still give an integer. So the factors of 42 and 56 are 2 and 14. So the greatest common denominator is 14 in this case. So again, we should have an example there that you can actually try out. Just click on there, and we'll take value 1 as 54 and the other one is 32. And the greatest common denominator is 2. So we've got some here as a reference. There's 14, and you can have a look at the algorithm that's used to be able to create that. But for 56 and 42 we have 14 there, as we've shown now. The other concept that we have is big integers or large numbers. So it becomes very difficult for a computer to operate anything more than 32 bits or 64 bits, because that's what its data bus size actually is. So the numbers that we normally use in programs are around here, but we in cryptography use very large numbers which can go on to 2048 bits. So that's what that looks like, and it becomes quite challenging. That's a 2048 bit integer. Okay, so we typically multiply these together, and we will and we do our operations on very large numbers. Okay, let's try and find our. Yep. Okay, so we'll look at some big integers. Okay, so there's some large numbers here, and we can see how big these numbers actually become. And these are the numbers that we multiply together. And in this case, I'm using a maths library with big integers. Another key concept that we'll come across is a random generator, random number generator. And we can have two of these. One is a pseudo-random generator, which is really created by a mathematical algorithm. It's fairly fast. Deterministic is that it will repeat. We can actually define a standard set of random numbers, and we can actually repeat them again if we do the same seed for the algorithm. And they're also periodic, so we can actually they finish and then they will start again with the same random number sequence. So for things like simulation modeling, then a pseudo-random number generator is great. For other things, we need what's called a true random number generator. It's fairly slow and will typically involve things like the keystroke analysis or the movement of the mouse by the user and so on. It's non-deterministic, and also it's aperiodic, so it'll never actually repeat. So these are two types. These are two random numbers that have been generated here, 122-bit and 128-bit. So you should be able to go to the web page and have a look at our random numbers here. So there's a random number generator for primes. There we go. Okay, so that's generating random prime numbers, and we should also have a random number generator here, which will produce our hexadecimal value. Okay, so you should just go through that. Eventually it will repeat, and we've even got a little JavaScript example here. So let's try and find it here. this is a little JavaScript. So JavaScript runs on the client side, and this is generating our random number generators. You can create this as a text format if it's easier, or in a hexadecimal format. As we've seen, that's 128-bit ones there. So we'll be looking at cryptography, and that will be important for keeping security, but a well-known method for actually defining integrity of data is called CR332. With this, we take our data and then we do some exclusive OR operations and so on, and we end up with a value at the end of it. The good thing with this is that we'll be able to determine any errors within our data as we actually send it. So in this case, the quick brown fox jumps over the lazy dog is a phrase that we often use to create a test, and then this has produced our CRC. We would send that with the data, and then on the other side they would actually take the data and check the CRC to see if they were actually the same. Okay, so have a look at this web page and you should be able to find some examples there. We have some test vectors that you can try out. So let's look at, we'll be doing this in more detail in the future units, but the problem with the methods that we've looked up to now is that it doesn't really work, because you can find out what the encoding algorithm is, and then really Bob and Alice would have to generate a new algorithm. What we typically do is we have a well-known algorithm, and even Eve knows about it, but we use a special key to be able for only Bob and Alice to be able to encrypt and decrypt. They have a problem in how they pass the key, but we'll see how that's overcome in a later unit. And the main methods that we have that we'll be coming across is what's called symmetric encryption. That's private key, uses the same key on either side to encrypt and decrypt. RC4, RC2, DES3, DES AES. We'll see public key encryption or asymmetric encryption, where we have a special key pair. One key is used to encrypt and only the other key can decrypt. RSA, DSA, LGAMO, and so on, elliptic curve, are the key methods here. And then we have a one-way function where it shouldn't be possible to mathematically go back to the original, and that's our hashing methods such as MD5 and SHA-1. We'll have a look at each of these methods in later units. Okay, as an example, let's say that we have a key and it has 4 notches. The notch can exist or not. How many keys can we actually have? Well, we can actually have 16 different keys, one with no notches, one with 1 notch there, and then last we have 4 notches, or 2 to the power of 4. So when we're looking at the number of keys that we can actually generate, is 2 to the power of n, where n is the number of bits that we actually have. So there we have here, and so there is 64 bits, gives us 1.84 with 19 zeros, and so on. 4 bits gives us 16 keys, as we said, and so on. So we'll go into this in more detail and when we look at our key generation. Okay, so that's been a very quick introduction to ciphers and fundamentals. In the next unit we'll be looking at public and private key and also into key exchange.